Welcome to our module on lenses. In this module, we will be looking at the types of lenses, various terms related to lenses, looking at the various lens formulae, how to draw scale drawings, and we'll be looking at defects of the eye and how we use lenses to correct them. So in our first lesson, we'll be looking at the types of lenses. So there are two main types. There are what we call converging lenses and diverging lenses. The main thing to remember about converging lenses is that they are fatter in the center, like your physics teacher. Here is a good meme. Yeah, I dedicate my life to the teaching of physics. Right? So biconvex lens, they are shaped outwards on both sides. A planar convex lens, which is like me, has one straight side and the other side outwards. And then we have the converging meniscus. The diverging lens is different from the converging lens in that it is thinner in the center. All right, so we have a biconcave, the planar concave, and the diverging meniscus, similar to the tree for the converging lens. There are many various terms that we need to learn about when it comes to lenses. First one is the optical center, which we denote as a capital L. It is the point midway between the lens surfaces on its principal axis. The rays passing through the optical center are not deviated. That is a special point in a lens. Whenever light passes through a lens, because it is made out of glass and because of its curvature, it will change direction, except for if it passes through the optical center. That is the only point where a ray will pass through a lens and it will continue in a straight line. The principal axis is an imaginary line perpendicular to the lens, and it runs through the optical center. The principal focus, capital F, is the point from which all rays parallel to the principal axis converge after refraction by the lens. We say that this focus is real, and this is only for a converging lens. Later on, when we get to a diverging lens, this definition will be slightly different. The focal length, small f, of a lens is the distance between its optical center and principal focus. The focal plane is the plane that is perpendicular to the principal axis and passes through the principal focus. It is where we say that the image is projected in focus. To show you exactly what these terms mean, let's look at this diagram here. So this is our lens, and right in the center is our optical center, capital L. Perpendicular to this and passing through L is the principal axis. You can think of these like your X and Y axes. That will be handy, especially when we do our scale drawings. Here, capital F, that is the point where all these rays that are coming in parallel to the lens will refract and converge at this point. We say that this is a real focus because these rays of light actually meet here. This is the focal plane. You can think of it in practical terms as a screen. When you have a projector where you actually project that image onto a screen, that is the focal plane. The distance from capital L to capital F is our focal length, small f. So this is how long or how strong a lens is, all right? Next, we have the definition for the principal focus, capital F, of a diverging lens. It is the point from which all incident rays parallel to the principal axis appear to diverge after refraction by the lens. This focus we say is virtual. Why is it virtual? It's because the light rays appear to come from this principal focus of a diverging lens, but in reality, they do not come from there. We hence draw these rays with dotted lines to show that they are virtual light rays. So this is a virtual focus. This is a diverging lens. Look at how the rays differ from this diagram as opposed to the previous diagram. With the previous diagram, they actually came together. That's why it's called a converging lens. Here in this diagram, they then spread out. That's why they're called a diverging lens. Okay? So next, we look at our lens formulae and how we calculate various distances and magnification as well. So our lens equation is 1 over u plus 1 over v is equal to 1 over f, where u is the object distance, v is the image distance, and f is the focal length, of course. When I was a student, I oftentimes would confuse what the u and the v stands for. But over time, I came up with a little thing to help me remember. And it goes like this. Alphabetically, u comes before v. And realistically, u, which stands for the object, must exist before we have the image, which is v. So that's how I remember the u is object and the v is for image. Key thing to remember here when using this formula is that if it's a converging lens, then your f, the focal length, is a positive number. Key thing to remember is that real is positive and virtual is negative. So when you have a diverging lens, then your f is a negative number. Our magnification equation, we have 2 in 1. We can use the image height divided by the object height or the image distance divided by the object distance. Key thing to remember is that it is image over object. So we have, in short, v over u. So let's look at an example. Our first example. Let's say Amberly and Zulema used their shoebox projector to watch Finding Nemo. The phone was placed 15 centimeters from the converging lens and the movie was projected 60 centimeters away on the wall. What was the focal length of the lens used in their shoebox projector and what was the magnification? So we identify our givens. The object u is 15 centimeters, the image v is 60 centimeters. Using these pieces of information, we can calculate the focal length of the lens that was used. So we have our formula, 1 over u plus 1 over v is equal to 1 over f. We substitute, we have 1/15 plus 1/60 is equals to 1 over the focal length. Using your calculator with the fraction function, 1/15 plus 1/60 is 1/12. But that 1/12 is 1 over the focal length. So then you have to use the reciprocal function on your calculator, and that will give you that f is 12 centimeters. You can do that using your calculator or by hand if you know how to add fractions. Next, the magnification. So we have our formula m is equal to v over u. So our image distance was 60 centimeters and our object distance was 15 centimeters. So 60 centimeters divided by 15 centimeters gives us exactly 4. And please note, there are no units for magnification. It is just a number. It tells us how much bigger the image was compared to the object itself. Example 2. An object was placed 37 centimeters away from a converging lens of focal length 25 centimeters. What was the image distance and what was the magnification? So as always, we begin by identifying our givens. U is 37 centimeters, V is unknown, F is 25 centimeters. We substitute into our formula. In this example here, we have to transpose and we subtract 1 over 37 from 1 over 25. Using our calculator, 1 over V will be 12 over 925. So then, using our calculator, we find the reciprocal of that and we get that V is 77 and 1/12 centimeters exactly. So the magnification then is V over U. Again, using the fraction function on our calculator, we take 77 and 1/12 and we divide it by 37, and that gives us exactly 2 and 1/12 magnification. So the image was just slightly twice as big, a little bit more than that. And in our third example for today, an object was placed 8 centimeters away from a diverging lens of focal length 12 centimeters. What was the image distance? What was the magnification? So we identify our givens, we substitute, but in this instance, we have to be careful that we have a negative number for f because it is a diverging lens. So when we transpose, we will have negative 1/12 minus 1/8. So the signs are the same. We actually add and keep the sign. And we then get negative 5 over 24 for 1 over v. Find the reciprocal of that, and we get that v is negative 4 and 4/5 centimeters. This negative sign that we get means that it is actually a virtual image. And that is actually the case for diverging lenses. Diverging lenses can only produce a virtual image. Then the magnification, we have m is equals to v over u. So negative 4 4/5 divided by 8 will give us negative 3/5. Here, we notice that our answer is a fraction, a proper fraction in particular. And all that means is that our image was actually smaller than our object. That is not always the case for a virtual image. It depends on what type of lens produces the virtual image. So now, practice on these two problems. Pause the video here. After you have finished practicing, then you continue. The answers will be revealed in 3, 2, 1. So I hope you did well on those two. After you have checked those, then do these two